geometry algorithms. We're not going to spend too many lectures on this. Maybe today could be the last one. We're going to go through some of the most famous algorithms that use geometric applications, namely convex hull. And yesterday we introduced this idea and talked about some of the low-level tools that we'll need in order to make higher-level geometric algorithms possible. And I just want to review what we did and give you some big picture and go through some details based on some questions I had yesterday that I want to make sure everybody understands. So the main thing we did yesterday as far as geometric algorithms is we discussed what they kind of were. They're algorithms that give points or line segments or polygons or geometric objects as their input and ask questions about them. So examples of geometric algorithms would be convex hull, a bunch of points. You want to get the border around those points. Another example would be I give you a bunch of points. Find me the 2 points that are closest together. There's all sorts of different algorithms. Give me a bunch of line segments. Tell me if they intersect, if there's two that intersect. Things like that. So we talked about a low-level helper tool that would help us do a lot of these algorithms, at least the ones that we're going over yesterday and today. And that tool was that if somebody gives you a point here and a point here and a point here, that we have a way of determining whether this vector is clockwise or counterclockwise from this vector. Okay, and that's relative to 180 degrees. So this one would be clockwise of this vector, and this would be counterclockwise of this vector. And that's a very important low-level idea because it allows us, in some sense, to compare angles. Another thing it allows us to do, besides just comparing angles, which one is, if I'm here, I want to know whether this is steeper than this, I can do it. Another thing it allows you to do, let's say I'm traveling along here. Here I am. And I come to the end here, and I see this point here, I see this point here, I see this point here, I see this point here. And I want to know if I'm traveling along this road and I turn over to this point, is it a left turn or is it a right turn? Right? That's really the same kind of question. If I'm here and I want to know if going here is a left turn, that's simply whether this vector is counterclockwise from this vector. If I want to know the orientation of this one, whether it's a left turn or a right turn, I can compare these two vectors. And if this one's clockwise, then going from here to here is a right turn. So if you're traveling along a vector and you hit the end of it, and then you want to know whether going to some other point is a left or a right turn, that can also be done with that basic low-level tool of taking two vectors and deciding which one is clockwise and which one is counterclockwise. And those two things, checking clockwise and counterclockwise and the ability to check if you're making a left and right turn, will be enough to help us raise up the level of discussion to a high enough level that I can describe these algorithms very, very quickly and easy to understand, rather than dealing with the low-level details of the x, y coordinates, which are now wrapped up in a higher tool. Okay? Let's review. Questions so far? So we talked about an algorithm. Doug, you had a question? No? We talked about an algorithm for convex hull that worked in a recursive way. And it worked like this. Somebody gives you a whole bunch of points. I figure out the leftmost one. I do that in linear time by just sorting on the x-coordinate. Not sorting, just by finding the minimum on the x-coordinate. And then I run my convex hull on the other n-1 points recursively, and I get a convex hull that returns. And now, my last step is the only step that takes any effort. I have to actually include this one in the new convex hull that I have. And the way to do it is to take all the nodes that are on my convex hull and to figure out, imagine this is I mentioned yesterday, like a crocodile. He's going to open up wide and chew up this convex hull. I want to get rid of all the points in between these two wide spots. So what are the wide spots? It's the angle that's the most in this direction and the angle that's the most in this direction. So all I need to do is calculate the angle between this point and all the other points. Calculate the minimum, calculate the maximum by doing these clockwise and counterclockwise comparisons. And the minimum and the maximum will be where the crocodile opens up and chews the other convex hull. And everything in between, you just get rid of. OK, like Pac-Man. How long does this take? Here's the time that it takes. There's a linear time step at the beginning, where you have to find the minimum, right? And then what do you do?
Recurse.
Then you recurse on n minus 1. And then what do you do? And then you do this. You do these comparisons. So the clockwise counterclockwise is a way for us to simulate what we used to do in sorting when we just compared one index to another index. We could check greater than or less than. Now we can check greater than or less than here too, but with respect to angles. And we mentioned yesterday that the worst thing we'd have to do is look at all these angles and calculate the min and the max, and that would give you something of order n. And when you solve this recurrence equation, you get order n squared. So that's a pretty straightforward algorithm that does convex hull, uses our basic tool, and runs in order n squared time. So Todd asked me yesterday after class whether this really had to be n. Because he said, well, look, you really only look at the points in the convex hull rather than all the points. You don't look at the points inside, right? Those are already taken care of. They're gone.
But all of the points can be on the previous convex hull.
Good point. So Todd's idea was that maybe this should be h instead of n. And I thought about it and thought maybe he was right. And then I thought about it a little longer. And I think that it really has to be n. And I want to make sure that we're all convinced it has to be n. And Sam really said the right idea. That at this point, it's true that we don't have to look at all the things inside. But what if there were nothing inside? What if the n minus 1 recursion actually had a convex hull that was everything? Okay? Then this would have to look at everything. But it's conceivable that when we're all done, the convex hull of the whole thing is still only 3 points. I'll show you an example. Say it looks like this. So the n minus 1 recursion gives you this. And now the last step has to look at all of these, which is really n. Even though it's the number of points on this convex hull, it's still n with respect to the whole picture. But more importantly enough, it's not h. H is the number of points in the convex hull that we end with. Look how many points in the convex hull we end with. Only 3. So it's possible that these subproblems might actually use linear time, even though they are just looking on the recursive convex hulls that we return. Because the recursive convex hulls that we return can be everything. And then when we're all done, everything might disappear. So it does give you a place to maybe try to improve this. It would be nice that this recursion wouldn't ever have this kind of pathological property. And maybe there's a way to fix this to make this lower. But we're not going to talk about that. This analysis is really order n squared, and it's not better. But we would love to get something. We have order n squared. We're going to talk today about something that's order n log n. We're going to talk today about something that's order nh, where h is the number of points in the hull. So it would be nice to get something like this. That would be a good result if we could do it. But this doesn't quite do it. This just gives you order n squared. Okay, questions so far?
Does this convex hull have an application? Do people use it for other things?
Oh, yeah.
What kind of things?
Well, I used it when I was programming Go. So people use it. There are a lot more, I imagine, practical applications of it than just programming a game where you're using it for an influence function.
Or you want to get the surrounding?
Yeah, I mean, I'm going to give a bad answer if I just guess off the top of my head, because I haven't actually worked on a project where this was like a fundamental piece of it. But I could imagine a lot of reasons why, if you have a lot of points representing anything, power plants, who knows what, and you want to figure out, some kind of theoretical border around the whole thing, or communication. Pieces of evidence in a crime. Well, then it would look like this. Right? His arm was pulled horribly out of the socket. So I guess, let me check, because I'm sure I could find out a very good example, but I don't really have one off the top of my head.
Remember something like you take statistical samples of people,
Mm-hmm.
and you want to know what the square mileage of all the people you talked to was, like what the area inside was.
Okay, so you have addresses of people that you talk to, and you plot them on a map, and you want to get the area of the place that you polled. That's completely reasonable. So you get this polygon, and then you approximate the area of the polygon by a various number of other methods. Yeah, that's a good idea. I'm not sure people do that, but but maybe they do. I mean,
You want a fence in your garden?
yeah. I'm just hesitant to say, look, it's I don't want to do this. I don't want to say, oh, there's just hundreds, even though I believe there are, because the same thing for sorting. It's probably as common in visual applications as sorting is in storing applications. But there's a lot more in visual processing than just convex hull. I mean, shadow tracing and all sorts of other things that are much more complex than this, because they really do use trigonometry and other linear algebra transformations. And this is pretty mundane compared to that. Okay. Other questions? Okay, one other thing we mentioned yesterday. I try to convince you that we're never going to do better than n log n. And in other words, that convex hull has a lower bound of n log n. That's the best we can hope to do. And the way I tried to convince you of this is, we all remember that sorting, if you use a decision tree model, has worst case at least n log n. We can't do better. We have a decision tree with n factorial nodes in the bottom, and the log of that has got to be at least n log n. So I want to convince you by a different argument that convex hull also has to be at least n log n. And the argument goes like this. It's an argument that you're going to see a lot in the last week. That's why I'm spending time on it. It's an argument that uses the idea of a reduction. What a reduction is basically a way to transform one problem into another. I'm going to convince you that if I could figure out a way to solve the convex hull problem, then I can also do sorting. So if you've got numbers to sort, I'm going to explain to you how to go to somebody who has a convex hull algorithm and get your numbers sorted. Therefore, if somebody's got a n-time convex hull algorithm, and I'm going to explain to you how to take your numbers and fiddle with them and then give it to that guy who's got an order n convex hull algorithm, and he's going to end up sorting your numbers for you, then you will have sorted your numbers in order n time. And that's not possible. Numbers take at least n log n to sort. Therefore, we would have proved that convex hull has to also take at least n log n. This idea is called a reduction. And the particular example we're doing, we're showing that sorting reduces the convex hull. Then I'll show you a way of solving sorting if I can solve convex hull. In other words, convex hull is at least as hard as sorting. And here's the method. It's very straightforward. Somebody gives me numbers. This is a review from yesterday. Say the numbers are 12, 3, 1, 6, 8, 19. I don't know the square of 19, so 16. And you want to sort these numbers. All right. You want to sort these numbers. Here's what you do. You turn them into points in a very fast step, and then you give it to the person with a convex hull algorithm. Here's how you turn them into points. You take each of your numbers and you square the x-coordinate. All right, 400 minus 20 minus 19, 361. I could do it. All right, here are the points. These points are given to the person with a convex hull algorithm. These points are points on a parabola, on the parabola y equal x squared. So they're going to be points along this graph. You give somebody a bunch of points, doesn't matter where they are, and if they can figure out the convex hull of these points, they're going to give you a list of nodes that'll go from here to here to here to here to here and then back. Now their list might not start at the bottom. Their list might start here. But their list is going to go in order, clockwise or counterclockwise. And you could easily look at the answer, find the smallest one, and then get your order from there. So the key thing is the slowest point in this process. How long does this part take? This part takes order n. You just go through each number and calculate its square. Finding the lowest one in this list of nodes people give you takes order n. The slowest point of this process is going to end up being the convex hull. So if they can do the convex hull in order n, then you figured out how to do sorting in order n. But you know that's impossible. There's no way to do sorting in order n. So there's no way anybody can get convex hull down from n log n. If they did, then we'd have a better than n log n sorting method. And that argument is based on this reduction, a way of taking sorting inputs, converting them to convex hull inputs, and having the solution to convex hull imply a solution to sorting. It's an idea that's going to be fundamental when we talk about NP-complete problems.
In doing convex hull, he's giving you the order of the points that make up the convex hull?
Yes, in some clockwise or counterclockwise order. That's the solution. When you get a solution to convex hull, you get the points in the order either clockwise or counterclockwise. The convention, I think, is counterclockwise.
So does this thing apply that you can do, like sorting, you can sometimes do in order n, right? If there's restrictions. Does that mean you can do the same?
You can't do sorting in order, unless if it's restricted, you can, right? It's some kind of restricted version.
So in that sense, the convex hull would also be restricted, right? So would that imply you could also do convex hull in order n?
No, it would imply that we wouldn't be surprised if somebody came up. If you came up with a restricted version of convex hull in order n, that wouldn't contradict this.
No, I know that.
Right, but it doesn't imply the other way. This is something that shows that if you can do convex hull, you can do sorting. But it doesn't show the opposite. It doesn't show that if you can do sorting, then you can do convex hull.
Yeah, but you should expect that that actually you can come up with an algorithm for convex hull in order n, if you know your points as limits within some given area or something.
Maybe. Maybe you can. But this wouldn't imply that you could.
No.
Right. I wouldn't doubt that you could, and it wouldn't contradict this result, and I wouldn't doubt that you could do it, but it's not implied by this result. Yeah.
Let me fill in one step that you're not verbalizing. If the points are ordered on the convex hull, then all you have to do is make a comparison between every pair of successive points, and the lowest one is going to be what we want. Whereas if we don't know about the ordering, you're going to have to make n log n comparisons. But here you only have to make n comparisons, you're saying.
You mean at the very end when it all comes back?
Right.
Right, of course. Right. Right, but I mean, if convex hull just sent you back the points in a random order, that wouldn't be so useful. They always send you the points back in the order clockwise or counterclockwise. All right, so let me, yeah, Neil.
Just why the direction of the inequality? Why sorting less than or equal to? How works that?
Because what this means is that if you can do convex hull, then you can do sorting.
Yeah.
It means convex hull is a harder problem than sorting, at least as hard as sorting.
How can you tell just from that diagram?
It's from the argument. It's that if you give me numbers that you want to sort, I've just showed you a way to do it with convex hull.
Yeah.
So if you could solve convex hull, you can definitely sort numbers. That means, therefore, convex hull is at least as hard as sorting. But it doesn't show it the other way. Just because you can sort numbers doesn't mean you can figure out a way to do convex hull. That may not be true. So we use this symbol for reduces because it has a less than or equal meaning, where this means harder than. Harder than or equal to this. Because solving this allows you to solve that, but not vice versa necessarily. Yeah, Joe?
Using convex hull that way, how would it work when you get negative numbers?
It's okay anyway.
Yeah, you just have
It comes on this side, right?
side of your parabola. Yeah.
You'll still have a convex.
You still got a convex hull, and you just run through the whole clockwise list looking for the smallest one, the one that's leftmost, and you'd still get an order. So it does work even with negative numbers. You don't have to do anything special. The whole argument works exactly the same, I think. Peter, you have a question?
Yeah, what's the minimum number of points to make a convex hull?
3. 3. There is, it's
Segments you do not have.
right. That it's not defined for 2 points, right? Other questions about this? So let me ask you a question. Now that everybody, Jacob, it kind of picked up on a subtle idea that he asked about, but kind of along that thread, what if I told you I came up last night with an algorithm that does convex hull in n times log h, where h is the number of points on the hull? Everyone understand? So a little better than n log n. Does that result contradict this lower bound argument? And if it does, why? And if it doesn't, why not? Everyone understand my question? For sure, if I came in today and said, I have a linear time algorithm, you should say, that's baloney. If you have a linear time algorithm, then this process would do sorting in linear time, and you can't do that in general. The question is, does this contradict that result? Rob, you have an idea?
I don't think it would, because if you're just doing points in the hull, then you're probably doing some kind of internal point elimination, which would constrain the set.
Mm-hmm.
And that would mean that for the things that you're still doing a convex hull scan on,
Mm-hmm.
you still have the same order of growth you would with Google search, but you're optimizing your set by
Mm-hmm.
3 times.
Good idea. Good.
On the
Yeah.
other hand, this particular reduction, n is always going to be equal to h.
Right.
Right.
So
Right.
that's not necessarily
Right.
contradicting our...
Right, good. I think everybody's got the right idea. This would not be a surprise. If I come up with this algorithm, and you look at this reduction says take the numbers, turn them into this. How many points are there on the convex hull in all these reductions? H equals n. It's always the same. So if I came up with an algorithm that did this, and I ran it in order to do sorting, it happens to take n log n for that sorting. In other words, this faster algorithm is possible because it won't imply any faster way for sorting. So you've got to be really careful in making judgments about reductions. It has a lot to do with how much time the reduction actually takes relative to the argument you're making, and it has to do with the special kind of instances that your reduction comes up with. Let me give you another example. If you prove a problem is very, very difficult or hard or NP complete, and your reduction instances all have a graph with lots and lots of edges, and somebody says, well, I have a really fast algorithm for planar graphs, which don't have lots of edges. And that's possible, because you've only shown that it's very, very difficult when the inputs are very unplanar. So you have to look at your reductions and see what kind of instances they come up with. If they come up with instances where all the points are always on the hull, then having somebody come up with an algorithm that's fast for when there's very few points on the hull, well, that's no surprise, because I've only shown you the convex hull is difficult like this, needs n log n, when all the points are on the hull. But when there's just a couple of points on the hull, or 3 or 4 points on the hull, maybe you can do faster. Maybe this is possible. So be careful with your logical deductions from reductions. And I think Rob and Chris hit it right on the button with the idea here. So this is possible. And in fact, by the way, you can do this. This is the best anybody knows for doing convex hull, order n log h. We won't go through that algorithm. It's a little bit tricky, but you can definitely get order n log h. All right, questions?
Many identical points on the hull are considered part of H as well as part of N.
Identical points on the hull?
You've given us unique numbers to sort on, but what if I given you 100 points?
All those points would end up just collapsing into... There's no way... I don't think you ever give identical points in a convex hull problem. Questions, points, anything about this stuff? Yeah, Chris?
The lower bound proof on sorting, is that specifically for comparison?
Yes, it's for decision tree model. That's true. And they were using the same model here, and if you use a different model, it's conceivable you can do better. Right.
Somehow don't compare like a counting sort equivalent of convex hole.
That's right. That's a very good point. That's an excellent point. Good. Good. Other questions, comments, thoughts? All right, let's play a game. It's a boring game, but it will help you later. All right, here's the game. We're going to count. 1, 2, 3, 4, 5. We're just going to go up the ladder. But I get to be the dungeon master, and I get to, anytime you guys get to a number, I get to make you go back down. Here's how the game works. So you count 1, 2, 3, 4, and now you're about to count to 5, but before you count to 5, I make you count down as far as I want. Now you can go to 5. Okay? And now before you go to 6, I can make you count down as much as I want.
1, 2, 3, 4, 3, 2, 5. Is that what you're saying?
1, 2, 3, 4. Now before you can write 5 down, I make you count down from 4 as far down as I want.
1, 2, 3, 4, 3, 2, 5.
1, 2, 3, 4, 4, 3, 2.
You have to repeat the 4.
Yeah. Yeah. It's, either way you like it. That's the rules. The rules are you can count down. I can make you count down. So before you get to 6, I can make you count down all the way back to 1. And then before you write 7, I can make you count down all the way back to 1 again. How many numbers will you count in the worst case? Sounds like triangle numbers, right? Because for 2, you have to count 1 plus 2. For 3, you have to count 1 plus 2 plus 3. Every time you go to the next number, you have to count all the numbers that are below it. So to get to 7, it takes 6. To get to 8, it takes 7. So it's 6 plus 7 plus 8 plus 9. Fine, it's triangle numbers. Triangle numbers are order n squared. Why am I doing this stupid game? There's a really good reason. In the algorithm that we're going to look at next, there's an analysis that we're going to do at the end. And if you don't look carefully at what the algorithm does, you're going to think the analysis can be like this. You're going to think it's going to be n squared. But it's really not. And I'm going to show you what it's really like in a game that's similar to this with a slightly modified rule. And it's that modified rule that really is what the algorithm is like. So this is a little prelim so that when we talk about it later and I describe it in 3 minutes and say, right, so it's order n, and you all think, I guess, and then 2 months later you say, oh, I didn't know it was order n. I thought it would be order n squared. I want to focus on it because it's going to fly right over it real fast and you'll think it's obvious and it's not. And then once you think about it for about half an hour, you'll say, oh, it really is obvious. So it's one of those. I want to heads up on the obvious here. So here's the other game. The other game is go as far as you want, like you were doing before. When you get to 5, I can make you count down, same as before. But now, I can make you count down as far as I want. So I'll make you count down this far. Now you put in 5. And now it's your turn to put in 6. And I can make you count down again, but I can't make you count down the ones that are crossed out. I can only make you count down ones that haven't been crossed out yet. Everyone understand the difference? It's a big difference. So I won't make you count down at all this time. I won't make you count for a while. Now you're going to do 11, I'm going to make you count down. I'll make you count down 3. Now 11 comes up.
So it's theta n.
Yeah, what's the worst here? 2n, right? What happens here? Here, every number gets put on when you're counting it on the way up. And in the worst case, you count it again once when I force you back down. But I can't make you do it more than one more time. So every number gets counted once. Once when it's written, once when it gets crossed out. That's the worst I can make you do. Even though if you're careless in your analysis, you'll say, okay, well at any point when I'm going to do the next one, the worst case is that he'll make me count all the ones that could be there. In the worst case, that's order n, right? Because they could all be there. And since I do n additions, the worst case would be n times n, which is n squared. But that cannot happen. You can't get that worst case showing up. This should remind you a little bit of amortized analysis. You can't get every worst case showing up. I can't make you, when you go to 7, do 6 countdowns, and then when you go to 8, do another 7 countdowns. If you do a lot of countdowns from 7, then you're saved from 8, from doing none. And if you have to analyze it, you have to analyze the whole thing in the big picture. The total number of countdowns you ever do is equal to the total number of things you put on. So the total number is going to be twice n, even though a naive look is going to make it seem n squared. All right. Think about this now. Get used to this game, because you're going to see this in the analysis of the algorithm, and then it's going to make some sense, and you'll know what I'm talking about if you've seen it in this somewhat simpler version.
Sean, how do you know when you're counting down that you can skip a number? Do you have a priority queue?
You can't skip a number. It's going to be a stack. When you count down from the top.
But do you mark things as having been visited?
You pop them off the stack. They're gone. So all the numbers you've counted are on a stack, and when I tell you to count down, you pop them off the stack. That's what really happens. Questions? And this is an order n log n algorithm. All right. The best way to do this is with an example. I have an example in the notes. You can just use that and look at it, and hopefully this will be a good enough one to give you a sense of the idea. Here's how Gram-Scan's algorithm works. The first thing it does is it finds a point to anchor itself on and to start at. Just like we used the leftmost point in my recursive algorithm before, he's going to use the lowest most point. So that's this one. I'll circle it. How long does it take to find the lowest point? It takes n, because it's a minimum calculation among the y coordinates. Right? So that's step 1. Find the lowest point. Order n. OK. By the way, if there are 2 points that are equally low, then you go to the left. OK, so you break a tie that way. It doesn't affect the algorithm. What happens next?
Who knows?
Yes, indeed. Who knows? I'm going to see how red my face can turn before we go on. If I was a true ninja, I could just increase the blood supply until it got completely purple. Okay. Gram-Scan, in the next step, is going to sort all these points in a particular way. It's going to sort them all by angle with respect to this anchor. I'm going to write that down. Looks like this. Okay? So this is going to be the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, from counterclockwise order. How do we do that? We do a sorting using the comparison of our clockwise, counterclockwise tool. And how many steps does this take? You're doing sorting. You're doing it on n different points. Whatever our comparisons were before get substituted for our xy tool. But the number of comparisons for sorting is n log n, and this takes n log n. So sort the points counterclockwise order with respect to this lowest point. OK, so now we've got order n, we got order n log n. So we got to do the rest of the algorithm with no extra time. Well, I guess we can do as much linear stuff as we want, but no more than n log n. So here's the next step. Gram-Scan starts by moving through these points in order, counterclockwise, adding points to the hull as we go. So at the beginning, it adds this one in for sure. It knows that has to be on the hull. It adds the next one in for sure because it knows that has to be on the hull.
Why do we have the second one?
The first two are gimmies.
First two are gimmies.
No, why do we have the second one? That angle may be correct, but that point may be much closer to the...
Yeah, the second one isn't free.
The second one is not free.
It's free for now. We might change it later.
Right, okay.
Yeah. What GramScan is basically doing is giving you the convex hull of all the points that it's seen so far as it goes in counterclockwise order. So if you just consider these 3 points, then they are definitely the convex hull of the first 3 points. By definition, there's only 3 points to a convex hull. Now what happens when I add this one in? These 4 points also make a convex hull. Oh, when won't I add it in? If I make a left turn to the next point, then it needs to be in the convex hull. Left turn. Left turn. Every time I make a left turn, it stays in the convex hull. But now, when I go to the next point, I make a right turn. A right turn means that I got something that's moving in. I got a pointy thing. Like I got punched here instead of moving out. So GramScan is fine with adding points if it's a left turn. But if it's a right turn, before it adds this point in, it has to do something. Here's what it does. It's standing on this point, and it says, oh, gee, it's a right turn here. I don't want to add that. So it backs up. It backtracks. Same question. If I'm standing at the end of this point, is it a right turn or a left turn to here? Left turn. Right. Left. Left turn. So you can add this one in now. You basically add a point in if it's a left turn, but if it's not a left turn, you back up to the last place you were and you see if that's a left turn. If it is, you take it. If it's not, back up again. Keep backing up until it's a left turn. Okay? So now I have this one.
Wait, isn't that order n squared? You can only go back.
Let's talk about that later. It's an excellent joke. That's what it is. All right. We'll talk about that later. All right. Let's see how bad it is in a minute. We're at this point. You're on this road. Here's the point. Is it a left turn?
Yep.
Yeah, it's fine. Here, left turn? No, right turn. You orient yourself down the road. Right turn. No good. I got to backtrack. Back out we go. From here to here, left turn? Yeah. From here to here? So you back out. From here to here, left turn, it's okay. Here to here, left turn. Here to here, left turn. And you're done. All right. In this example, we didn't have to back out too far in any of the situations. But I could easily come up with an example where you would have to back out pretty far in some situations. Here, the worst case we have to do is back out once. But it's perfectly conceivable you'd have to back out 2 or 3 times. That's his algorithm. Start out with 3 points to start. Add a new point into the convex hull as you sweep in a radar scan from clockwise to counterclockwise. But if it makes a right-hand turn, don't add it in yet. First backtrack and throw a few of the things you already had in before off. OK. Questions about how it works? Who gets it? Mike, you get it?
Oh, yeah.
Oh, yeah.
Clear as mud.
Clear as mud. All right. How long does this take? How about this? I got a better idea. Before we say how long it takes, make you guys do something. Joe, you're up. Here we go. Let's try to come up with an example where we have to backtrack, say, more than twice.
Take
down one line, just put it way up top.
Which line put it way up top? This one?
Make the
next one,
initial line and the
that one.
last line.
I want Joe to do it. This one, way up? That one?
Yeah, a little further, I think.
All right, so. All right, here, here, here. This one is here. This one is here. This one, like up here?
Yeah. And move the first point out.
Like this? Will this do it?
No, and you got to move the first point, the first gimme, out further.
Out here?
No, this way.
Out this way?
That way.
How far? Like way over here?
Yeah, like right there. Over there.
Okay. Now let's try this. So now I got to order these, right?
No, no, no.
No?
Not that point. The point, right. The other. That point.
This is the bottom?
That's not the bottom. Put the bottom back where it was.
Back where it is. How about that?
Good.
All right, let's try this. So I'm going to make the ordering again. Here's 1, 2, 3, 4, 5, 6, 7, 8. NBC. All right. You get this for free. This is a left turn, right? And this is a left turn. And that's a right turn.
Right.
So now we got to back out. And that's a...
Left turn or straight.
I think it's a right turn. So I think we have to back out to here. And now it's a left turn. And this is a right turn. So we got to back out again. And now this is a left turn. Sound like that? Okay, good. So we got 2 backtracks here, and we got a second backtrack to the same spot. And now it's a left. Now right. So we backtrack to here, then left, then left. So there is a double backtrack there. If you try hard, you can come up with a situation where you have to backtrack all the way at the last step. But how many backtracks altogether? That's the question, and we're going to analyze it. All right. It's exactly like the game we just played. Every time you try to move counterclockwise, you're trying to add 1 extra node. Every single time, you will always add that node to the convex hull. Just like every single time when you're counting 1 higher, you're always going to get that next 1 higher, 7 or 8. But before you do, before you add that next node to your convex hull, you might have to backtrack and take off nodes that you're already on your convex hull. So if I label these nodes as A, B, C, D, E, F, let's make a list of what's on the convex hull. It starts out A, and then B, and then C and D, and then what happens? And then D goes off, and C goes off. B stays on, and then you can count the 5th one, namely E. Before you get to F, though, you have to take E off. It's the same counting scheme we did before, except here it's just letters or node numbers. And once you've taken something off, you never have to take it off again. It's off forever. And you only put something on once. So the number of times you actually deal with any one of these nodes is twice. Once when you put it on, and once potentially if you're forced to take it off. Twice altogether. So the number of times you ever do manipulations of these nodes is twice each node, which gives you order n. Now, the reason it feels like order n squared is because at any stage, you might have to backtrack all the way to the beginning, which is n possibilities. But if that happens, then you're guaranteed that the rest of the time you get for free. You're not going to ever have to backtrack after that. So the sum of all the backtracking can never be as bad as n squared, even though each particular case of n could be as bad as n. They can't all be as bad as n together. Does that make sense? OK. How do you actually implement this? Since the ones you're getting rid of are the ones that you most recently put on, you use a stack. So the first 3 get thrown on the stack at the beginning. They're initialized. And then you go through looking for left turns. If you get a left turn, you push 1 on the stack. If there's no left turn, if it's a right turn, keep going through the nodes, popping them off the stack until you get a right turn with the 2 nodes that are on top of the stack and the next node that's on the list. When you get a left turn, you put it on. If it's a right turn, keep popping things off. And that's the algorithm. It takes order n for this last step. I'll call that processing. Scan processing. Going through the whole thing. It's a clever idea, and you should get used to this because it comes up a lot. The idea of analyzing something as a group rather than each of the iterated cases being the worst case. Because it happens a lot that you get a better complexity if you consider it as a whole than if you consider each iterated case separately. Okay. Questions about this? Yeah, Doug.
We've got 2 points that are along the same line. So for example, between B and E, there's another point that's exactly along that line. Would that point be along the convex hull?
Like if there were a point here, for
B and F. Yeah, whatever. Between any line.
Say there was one here.
Yeah. Would that point?
It would be on the convex hull, and what would actually happen is that it would be not a right turn or a left turn, it would be a straight line. Right. So what we really look for is if it's a right turn, pop. But if it's not a right turn, then go ahead. I have this sneaking thing whispering in the back of my head that in my notes, in writing the loop of this code, I might have goofed up left and right. I got this, you know, like you left your keys on your desk, that kind of a feeling. I just got this feeling that maybe, when you ask this question, that maybe instead of saying, keep doing it until it's not a right turn, that I might have used the word left. I got to go check, but double check that just in case. All right, questions about it? Did I do it? Did I make that mistake?
While a left turn is not made.
Oh, that's good. I did do it right.
No,
It's not, it doesn't count 0.
Yeah, well, you do say, well, left turn.
It doesn't matter whether you count 0 or not.
No, we want to include the point if it's 0. So I say if a left turn is not made, that means if it's straight or if it's, no, I said it wrong.
Yeah.
I have to fix it. Okay. As long as it's a right turn, you want to pop. If it's a left turn or straight, you're ready to stop popping and put the new one on. I got to go fix it. All right, yeah, Neil.
Sorting seems so easy to do visually in this thing, that, you know, compared to other sorting problems. There's no way to get it faster than n log n? Just to get those in order, to know which one is the
You know what I mean? Yeah, you mean like instead of doing it in the computer, just put these on some kind of a phosphorus light screen and run some laser beam and see which... I'm not joking. I mean...
Pivot a ruler around A until it hits another point.
Right, or do that electronically. Right. It brings out a good point. The point is that our model of computation here is a computer and a machine language that the computer's running on. And perhaps there would be a better machine that could sort these in linear time that didn't use that model at all. That's really the notion and the gist of leveraging DNA to do that, rather than just leveraging a ruler or an electronic laser. Maybe we can just encode these things in molecules and let the wonderful parallel world of biology solve it for us. I mean, there's a whole world of other computation models out there, and limited only by what quantum mechanics, you know, stops us from doing at the lowest level. And it's a good question. I don't know if any research has been done in that direction, but perhaps it has. I don't know. Yeah. Other questions? Okay. Enough a gram scan. That's an n log n algorithm. You'll notice that n log n algorithms come up in different ways. In this example, it came up because we did a pre-processing step. We did a sorting step that was the whole time sink of the algorithm. Everything else was actually, even the complicated stuff was easy, complexity-wise. There's other ways to get n log n. The other ways to get n log n is by doing a split recursively of the problem in half and doing a linear time gluing, like merge sort, like the good case of quicksort. We haven't talked about that at all, but it's something you should think about. If I did I'm not going to go through the details, but it's an interesting question. I didn't give it for any homework, but just something for those of you who like thinking about these things. What if there are a bunch of points, and I made an algorithm like this? I split the points in half. How do we do that? I don't know. We got the convex hull of each side. And now we merge the convex hulls together. So there's two issues. How do we split the points in half? So there's as many on the left as on the right. And then, how do we merge them together? Which do you think is harder? Merging these two together or splitting them left to right? Merging them? So then you have an idea of how to split them left to right? Find the median. Find the middle one of the x coordinates, and then just go left from there. And okay. Will that work? That takes linear time. Find the median, right? We can do that.
If you split them that way, could you just merge the highest and the lowest points on either side? If you split it.
What do you think? Can you merge two convex hulls by just finding the highest and lowest points of each one and getting rid of the other points?
No.
Can you give me a counterexample?
Sure. In this case, if you had, let's see.
If the one on the right, the top point on the right was extended beyond the angle of the upslope on the left, so right up at the ceiling, then you wouldn't. Then you'd have to redraw the left hand.
I'm convinced you understand what you are saying.
There's a point here,
Yeah.
and then there's a point here.
Mm-hmm.
This point would have to be on the convex hull, but if you just merge the lower ones, you would do that when we really want.
Agreed. Good. Right. It's possible this could be actually higher, but needs to be on the convex hull. So
So it would have been on the other one, but it still would have been the lowest.
it would have been on this one. That's true, but this one could be lower, even though this would be the one we'd see. So it's a very good first try.
But we could.
But it doesn't quite work.
Work left or work.
Oh, so okay, and then maybe we could do an angle thing. All right, so
Save on that.
I'm also convinced that if I set you loose on this problem for a few minutes, you would figure out how to do it. But back in your cages. Lunchtime is later. You've got plenty of problems to look at. Good, you made a lot of progress on that in 30 seconds. It's key to try something that doesn't necessarily work and see what's wrong with it. It's very important not to be afraid to do that. Really important. That's how you make things work. Let's move on to another algorithm that isn't n log n, that isn't that splitting in half, called Jarvis's algorithm. And this runs in order nh. And this is really easy to describe. This is not tricky at all in its analysis or in its implementation. So similar to Graham's algorithm, this is the last thing that's similar in this example. You start with the lowest point, and if there's a tie, you start left. So you start here. And the idea of this algorithm is actually similar to something Rob mentioned the other day about kind of like trying to wrap around the convex hull. Imagine that you just stuck a piece of tape here, and we're going to wrap the tape around. Now, how do we do that? Where's the first peg it should wrap around? How do you find it? In terms of left and right angles. How would you describe the point? It's the rightmost angle, right? That's easy to do. How much time does that take? It takes linear time to find the rightmost angle, the one that's most clockwise. So you include that.
Can it also be the leftmost angle?
Yeah.
Okay.
Absolutely. We're just arbitrarily going in this order. The reason, well, yeah. I said we break ties by going to the left, so that's why we move to the right. If I broke ties by going to the right, we could move to the left, and it would work just as well. All right, so now what? Now I'm here, and I want to figure out what to do. So just change your orientation. Stand on this spot, and find the rightmost angle relative to this spot. It's really straightforward. There's nothing to it. You just keep changing where you're standing and look for the rightmost angle. The rightmost angle standing here is this one. Now you stand here. The rightmost angle is this one. Uh-oh. Now you stand here. Then you stand here. Then you stand here. And then here. That's the algorithm. Okay? How many steps does it take? Every time you're looking for the rightmost, it takes linear time. You have to look at all the nodes and find the one that's the maximum, the most clockwise one. How many times do you do that? Proportional to the number of nodes that end up being in your hull. It's easy to analyze, easy to state, easy to code. It takes order NH. The interesting thing about this algorithm is that if the number of points on the convex hull is very small, if it's going to be 3, for example, then this is a linear time algorithm. If it's going to be n, then this is an n-squared algorithm. So just like with graph algorithms, we always have the distinction between e log n and n squared, and we have to decide which one to use. And this one is better when you have very few edges, and this one is better when you have a lot of edges. Here too, this is better when you have very few points on the convex hull, and the other one's better when you have a lot of points on the convex hull. So you can't compare them directly without knowing how many points show up on the convex hull. And it depends on your application, and it depends on what comes up in practice. Okay. Questions about Jarvis's algorithm?
Do you stop when you get back to the point you started?
Yes.
Why continue?
How does it?
Why? Well, we could continue. Yeah.
If we run into several line segments that are the same angle, do we just then have to figure out which one's nearest and go to that?
Good question. What happens if we have one right here? So at this point, the rightmost is this one and this one. Take which one?
Actually,
It has to be the shortest.
You have to break the tie in a careful way. You can't break the tie by saying, lowest one or leftmost and rightmost, because our orientation changes all the time. So how do you break the tie?
You have to figure out the magnitude.
By which one is closer to you. Right. So you do have to be careful about stuff like that.
But it really doesn't matter. You can simply define out any point that's on a previous line.
Right, but in practice, this is going to actually be sending back a list of points. And if we left one off,
They all would still be the same. You just wouldn't have named the point that you're going through.
yeah, the hull from the point of view of the edges are the same. But it's conceivable that the hull points actually represent things that you want to process later. And if we leave one out by accident, we wouldn't be able to see it. But you're right. I mean, the actual geometry would be the same, but we might lose some data or some things we want to look at. Like, for example, if it were a Go game, we would actually lose a stone that we otherwise would know was there. And we could reconstruct it by looking along the line and seeing if it was there, but that would take time. Other questions? Okay. Switching topics. We're starting on a new topic. I want to switch gears from applications. There's plenty more applications to talk about, but we don't have time to do them all. So I'll leave string matching for recitations, for advanced recitations, and let's move over to thinking about algorithms by technique rather than by application. The good news is that when you think about it by technique, every technique comes up in all the different applications. So I'm going to use this opportunity whenever possible to talk about the applications we haven't done so far. So I'll use one from parsing, which you've never seen an algorithm for. I'll use one from mathematical algorithms and matrix multiplication. We'll use another from graph algorithms, which will expand on the shortest path idea. So we'll take them from a hodgepodge of different applications, but we'll be focusing on the techniques rather than the application. Okay. Let's start with this topic, dynamic programming. Okay. Dynamic programming is neither dynamic nor programming. Discuss. It's the worst name for this thing. Programming, the name was invented a long time ago, and programming was used in the sense of making a table, and filling in the table. And I don't know why they use dynamic. It's a bad name, but from now on, just disassociate the name from any English words you're used to, and think about what I'm going to say right now. And from then on, dynamic programming means that.
What would be the better name?
Frank.
What would be a better name? Once you know what it means, it doesn't matter. But what would be a better name? I'd say bottom-up processing is a better name. Okay? Let me show you what I mean. We're going to go back to a fond friend, the Fibonacci numbers, for a minute. Yes. We haven't visited them at all this year, and they're lonely. Here they are. Fibonacci numbers are defined this way, as you all know. And the first two Fibonacci numbers are both 1. And then they build up. 1, 1, 2, 3, 5, 8. God knows you've seen a million versions of these. You've solved this recurrence equation, blah, blah, blah. Now let's think about it from the point of view of an algorithm. Let's say I wrote a recursive algorithm. Dynamic programming is always the flip side of recursion. They fight each other for which one's the right one to use. If you write a recursive algorithm for doing Fibonacci, then it looks something just like the recurrence equation. Fib of n, if n equals 1 or n equals 2, return 1. Otherwise, return fib n minus 1 plus fib n minus 2. Okay? So whatever language you write it in, it looks more or less like that. And that's a recursive algorithm. It's 2 lines long. It mimics the recursive definition. Let's see how bad this is. This is horrible. If you do this, in fact, I have it on a talk I once gave. I wrote this in a scheme dialect. We put in 40, and it sits there while I give the talk looking like this. 40 minutes or so. I mean, a long time just calculating. If you calculate the 40th Fibonacci number in a different way, it spits out the answer instantaneously, virtually. What do I mean a different way? Well, the obvious way. How would you normally calculate a Fibonacci number? You'd start at the bottom. You'd say 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. You work your way up, getting a new Fibonacci number with every new addition. How long should it take you to get the 40th Fibonacci number? 40 additions at the most, 38 additions. How long does it take you to do it this way? It's horrible. Let's see. Fib of 40 turns into Fib of 39 and 38. Fib of 39 turns into 38 and 37. 38 turns into 37 and 36. 38 turns into 37 and 36. 37 turns into 36 and 35. 36 and 35. 35 and 34. A good way to imagine how completely absurd this is to pretend you are the compiler or you are the recursion master, and every time you get recursion, you hand off subproblems to your friends. So I'm trying to do Fib of 40, and I get my friends together. I got a lot of friends. Get 10 trillion friends. And I say, you do Fibonacci of 39, and you do Fibonacci of 38. And they go, how do I do that? I go, get your own friends. And then I go, you can take some of mine. So they look at the 10 trillion, and the 39th says, okay, you do 38 and you do 37. And the 38 says, you do 37 and you do 36. So what happens when you do this is you get this ludicrous amount of duplicate computation. It's hideous how many times Fib of 35 actually gets evaluated. And it's even more hideous how many times Fib of 2 is going to get evaluated. There's going to be millions and billions of people calculating Fibonacci of 2. Well, yeah.
But your 10 trillion friends will be able to do it.
They would. I mean, in fact, 10 trillion would do it. Right. Just barely. All right. So this is the wrong way to do it. What clues you in that it's the wrong way to do it besides me jumping up and down and yelling and screaming? What clues you in is that the subproblems repeat themselves. When recursion ends up getting lists and lists of subproblems that are all the same, you should be very, very concerned, and you should ask yourself, maybe there's a better way to do it. Let me warn you, sometimes there isn't a better way to do it. Sometimes you're just dead, and the problem's hard. But if you're getting lots and lots of duplicates, you got to ask yourself, is there a better way? Recursion is not appropriate if your subproblems start repeating, especially if they repeat an exponential number of times. That's where dynamic programming comes in, with its bad name and all. If recursion is a top-down process, right, top-down, then dynamic programming is a bottom-up process. It starts at the small cases and works your way up. The key thing about dynamic programming is, if you didn't get duplicates, then top-down and bottom-up would be the same. Who cares if you start at the bottom or the top if there's no duplicates? You still got to do everything. But if you have duplicates, bottom-up is a good way of making sure you never hit anything twice. In the case of Fibonacci, it's the easiest thing to describe. For I equals 1 to 40, Fib of I equals. All you got to do is keep two temporary variables. Start the first one at 1, the second one at 1. And let the next Fibonacci number be the sum of the previous two. So let's start this at 3. We'll set Fib of 1 equal to 1 and Fib of 2 equal to 1. And for I equal 3 to 40, Fib of I equals Fib of I minus 1 plus Fib of I minus 2. These are not recursive calls. These are accesses to an array. Right? So all this does is look back the last two slots, the last two temporary slots that I used, and gets me the next one. After 40 iterations through this loop, I have Fib of 40, and it's right. What did I do? I made sure to calculate every single subproblem. Every single one I calculated from the lowest to the one I wanted, and I did them in a particular order to make sure I didn't duplicate any. As simple as this seems, if you get this paradigm in your head, you'll have a much better understanding of the more complicated dynamic programming algorithms that are going to come up. Dynamic programming is simply a bottom-up version of recursion where you avoid duplicate calls to the same subproblem. The key to avoiding duplicate calls is being able to do the subproblems in some particular order, and typically from the bottom up, where the bottom is defined to be the ones that are necessary in order to do the ones that are coming up. In this case, you start with 1 and you move your way to 40. There's going to be a lot more complicated examples of this, so get the gist of it right now. Questions so far? So the recursion example for Fibonacci is the complexity of this recurrence equation. Remember what the solution for that is? It's like 1 plus square root of 5 divided by 2 times 1 over the square root of 5 to the n plus 1. Some ugly exponential. Very, very slow. And the complexity of this is order what? Order n, order 40 in that example, right? So you knocked it down from exponential to linear. Jeff?
Does dynamic programming have anything to do with memoizing?
Does dynamic programming have anything to do with memoizing for you scheme learners? It's got a lot to do with it. In fact, if you just substituted in your head that idea, you would be doing just fine. But there is a subtle distinction that's really just minor. In memoizing, What really happens is you do the thing recursively, and every time you calculate a subproblem, you store it somewhere. And before you do any more recursive calls to that same subproblem, this one, for example, first, you wouldn't do it because you've already done it before. You'd look it up instead. So memoizing kind of implies a recursive algorithm where you do lookup rather than extra recursive calls. In dynamic programming, you start from the bottom up and you store it explicitly. Very similar, just a minor difference in the implementation. But it's very much connected. Other questions?
I was noticing that if you look right or left and say which is the lesser computation, you could do that a sort of relaxed path graph algorithm kind of thing with this tree over here. And in that way you would basically memoize an order. And then you'd actually
You're trying to describe a way of pruning through this tree so that you don't hit any of the duplicates? Is that what you mean? Yeah. That's basically what memoizing tries to do with the lookup. And that would avoid this. Yeah. Okay. Questions about this? Right. I want to do one other simple example, then we'll quit for today. And I'll leave complicated examples of dynamic programming to come. Like I said, we'll do one mathematical algorithm, we'll do one graph algorithm, we'll do one parsing algorithm. The only one that's not in your book is the parsing algorithm. So I'll put that in the notes, and I'll make sure to be very careful with the board that day so you can get all the details. But the rest you can get a lot of good references for. One more simple example before we quit is something that you've also seen many times before. Pascal's triangle and what are called binomial coefficients. If you're looking in the nth row and the mth column of Pascal's triangle, you get the binomial coefficient n choose m. For example, 5 choose 2 is going to be 10. 5 choose 3 is going to be 10. 4 choose 2 is going to be 6. Right? And this, there's a recurrence equation for this. If you want the binomial coefficient n choose m, it's the sum of the two things on top of it. It's n minus 1 m plus n minus 1 choose m minus 1. We talked about this a lot in discrete math. There's a combinatorial way to think of this. There's a mathematical way to think of this. You can write out the factorials and add them up and show that it works. There's a million different ways to think of this identity. But all this is no more or less than a recursive relationship. This is based on smaller instances of the same thing. And you can write a recursive algorithm to do this. You can say, I want to calculate b of nn. What's the base case?
0, 0 is 1. 1, 0 is 1. 1, 1 is 1.
Anytime the bottom is 1, there's one way to choose it, right? That's true also. Anytime the bottom is 0 or the bottom is 1, there's one way to choose. So you can stop at 1 or 0. What's going to happen here? These guys are all going to get lower and lower. These guys are going to get lower. Let's see what happens. Let's start here and see what happens. These two depend on these two, right?
When m is 1, isn't there n to choose? 40 choose 1 is 40, no?
You're right. I'm wrong. N choose 1 is n, not n choose 1 is this row. Right. Right. Correction. Sorry. Let's follow this back. 6 depends on the 2 above it. 3 depend on the 2 above that. And this 3 depends on the 2 above that. That's the first duplicate recursive call. They both require you to calculate the binomial coefficient of row 2, column 2. This better not depend on anything. This has to be a base case. Right? What's this base case represent? It represents when n equals m. So that's one base case. What does this base case represent? When m is 0. So 2 base cases. If m is 0 or m is n, then return 1. Okay, that means you've hit the edge. Otherwise, if you haven't hit the edge, then there's 2 things on top of you, and you can go upwards. So you're going to return, just look what it says, n minus 1m plus n minus 1 m minus 1. That's the recursion. If you run this recursive routine, it gets pretty bad. You get all sorts of duplicate recursive calls. Here you see the first example of it. 6 calls these 2, and 3 and 3 call these, and that one gets duplicated. If you start lower down, the duplications get even worse, just like with Fibonacci. This is a horrible way of doing it. How horrible is it? Let's try to figure it out. In this example, unlike the other recurrence equations, we have 2 inputs. So let's consider the size of the input to be the sum of these 2. So let's calculate how much time it takes to do something that has n and m. I'll call it size. The time it takes to do something of size n plus m is equal to the time it's going to take to do this one and the time it's going to take to do this one. This one has a size 1 less, and this one has a size 2 less. So here's a recurrence equation for the time it's going to take. That recurrence equation is exactly the same as Fibonacci numbers. So this is just the same kind of bad thing in disguise. If you take binomial coefficients and you actually calculate them recursively through this recurrence relationship, you get a horrible situation. You get all sorts of duplication. The time it's going to take to get that duplication is just as bad as doing the Fibonacci numbers. All right. There's something a little bit different about this case, though. Let's say I started, 1, 6, 15, 20, 15, 6, 1. Let's say I started at 15. And I was doing this recursively. What are the first 2 I calculate? I got to do these 2. Then I got to do 6 and 4. Then I got to do 4 and 1. Then for this I got to do 3 and 3. For this 4 I got to do 3 and 1. For this 3 I got to do 2 and 1. For this 3 I got to do 2 and 1. Things just propagate their way up, get lots of duplicate solutions. But at least, and a lot of people feel good about this, and that's why they do this recursively, at least I didn't have to do these. Right? At least unlike Fibonacci where you always have to hit everything, here at least there's a sense that you're threading your way efficiently through the triangle, only looking at the ones that you actually need. The problem is you get all these duplicates. So when somebody first sees the alternate solution to this, what's the alternate solution to getting this value 15? It start at the top and just use a 2-dimensional array and work your way down 1 row at a time. And every time you go through, you have a line like this. Instead of it being a recursive call, it's just filling in a value in a 2-dimensional array. And you just go for I equal 1 to n, for j equal 1 to m. It takes n times m. It's very fast. The thing about it is that you have to do this one, and this one, and this one, because the only thing we're going to do is go through it randomly, or stupidly, left to right, row by row. So that's a common trade-off in dynamic programming versus recursion. You have to do every subproblem to make sure you don't miss any. So you end up doing ones that are completely irrelevant to your answer, but you only do it once. So even though here you've threaded through more efficiently, the duplication is horribly exponential. You're better off doing everything exactly once, even if it means doing things that never actually affect your 15 directly. Everybody get that idea? I think you can see it in the binomial example here better than the Fibonacci. This idea comes up in other problems. Fibonacci doesn't have this idea at all because you always do all the subproblems. All right, so I'll stop. Any questions about this? I'll try to review this next time again. I got too many I'm tired looks in going over it. So I'll go through this again a little more carefully, and then we'll bridge ahead to a real problem that we actually solve with dynamic programming.